Okay, so our next speaker is Changcheng Miao. He's a researcher and engineer at Tencent. His research interests include optical networks, wide area networks, and cloud networks. So go ahead.
Okay, hello everyone. I'm Changcheng Miao from Tencent.
Use the microphone, please.
Oh, okay. Okay, hello everyone. I'm Changcheng Miao from Tencent. Today I'm going to share our mega-scale WAN traffic engineering at the granularity of the virtual instance. The title is MegaTE, extending WAN traffic engineering to millions of endpoints in virtualized cloud. This work is collaborated with MIT, Northwestern University, and Peking University. As one of the world's largest cloud provider, Tencent Cloud allows millions of tenants to run virtual instances at the virtual machines, containers on the same data center. With the same data center, such cloud paradigm allows cloud tenants to achieve cost sharing benefits. Cloud provider always own and operate wide area networks to connect those data centers. To connect those data centers to provide service globally. Therefore, WANs are the workhorse of the millions of virtual instances with the exchange of terabits of data every day. Those cloud applications may have different requirements of quality of service. For example, Q's class 1 always is the highest priority with 4.9 service level agreement. It includes essential network control traffic and some critical financial service such as financial service. Those applications are always time sensitive, and the Q's class 3 is the lowest priority. It contains large bank transfer. A natural question we ask is how to provide network resources in a way that align with the specific needs of each virtual instance. So in this talk, I will present a first of its kind system, a MegaTE, that extends T system to meet the instance-specific requirements of millions of virtual instances. Let me start with the background. In the conventional T systems, the router collects the traffic metrics from the from data center servers in an aggregated fashion and then sends it to the bandwidth broker. The bandwidth broker forwards network topology and traffic demand to the T optimizer, which calculated the optimal path for the, and then SDN controller receives the configurations and adopts the top-down centralized control to push the configurations back to the router. And to enable the immediate synchronization of the T configurations, a persistent connection is established for each router, and to maintain the connection, a heartbeat packet is periodically generated and exchanged to keep it alive. So obviously, the conventional T system operates on the routers. They are not able to distinguish network traffic generated from the container, resulting in that network resources are able to align with the specific needs of the router. Specifically, there are always multiple traffics generated from the same container, entering the WAN through the edge router. The hash function of the traffic spilling in the router may route the traffic into different paths. This would result in that those flows have different packet latency, harming the application level performance. We measured we measured the packet latency for instance from the production. It shows that a large variance and is not stable. We zoom in one of the instance pair. We can say that the latency is mostly clustered into 20 milliseconds and 40 milliseconds. Ideally, TNets requires a flow between the instance pair to be running on the low latency path. To address this issue, our goal is to extend the existing T system to involve millions of virtual instances. In this way, despite of the complex cloud environment, we can precisely accommodate to fine-grained requirements for each virtual instance. However, it's not trivial to achieve this goal. If we assume that each traffic flow of the TNets can be distinguished on the router by inserting the flow entries, accommodating millions of virtual instances requiring installing millions of flow entries in the router. However, the number of the flow tables in the router is limited and always static. It's not practical to install flow entries. Therefore, the flow should be identified and segment routing. Information should be inserted before the flow leaves the server. Another challenge is the computation complexity involved in formulating optimal T decision at the control plane. The traditional T system manages the traffic at about a few thousand nodes. In our MegaTE scenario, it must manage the traffic of between millions of endpoints, magnifying the problem scale by 3 orders of magnitude. It's hard to solve the T problem in a timely manner without compromising the accuracy. Furthermore, conventional T systems adopts top-down control loop that uses the persistent connection to push the T configurations. When extending the control loop to millions of endpoints, a conventional control loop will require millions of persistent connections at the controller. This approach consumes a lot of resource and overwhelms the control plane. So to address these issues, our MegaTE system includes 3 parts, including the re-architecting the T control loop, a 2-stage T optimization algorithm, and an ePBF-based segment routing. Okay, to address the control loop issue, MegaTE re-architects the control loop by trading data plane consistency for control plane scalability. Specifically, it uses a bottom-up approach in which the controller is replaced by the T database. So the endpoint server pulls the configuration asynchronously. This approach does not introduce much overhead at the controller, since it doesn't need to establish millions of persistent connections with the T controller. Specifically, the T optimizer updates the T configurations and stores them into the database. Those endpoints queries the cloud database to check for the latest version. Upon detecting the discrepancy between its current configuration and that provided by the database. The endpoint will pull the new TE configuration and proceeds to update its setting accordingly. Those endpoints will coverage a consistent view of the network states over time. Okay, as the control plane, since we address the TE problem as the granularity of the virtual instance, we assume that traffic flow from the virtual instance cannot be arbitrarily divided. The main reason is there are always several flows between the endpoint pair. Routing those flow from the same TNet over multiple paths will introduce different latency. Degrading the application quality of experience. This turns the conventional multi-commodity flow problem into an NP-hard decision problem. The hyperscale network topology and an NP-hard nature makes the max-O flow problem extremely complex. Fortunately, we observe that in MegaTE topology, it consists of two distinct layers of connectivity, where the first layer is a highly matched topology among network sites, and the second layer includes the network sites forming a hub that connects to multiple endpoints. Therefore, we propose a two-stage optimization algorithm to solve the problem on each layer separately. Okay, on the first layer, we first aggregated the network traffic from the router sides and solve the max site flow problem. Since those flows at the router sides can be satisfied in part, so it becomes a multi-commodity flow problem, and the number of the nodes is a few hundreds. We can use the existing TE schemas to obtain the bandwidth allocation. In the second layer, we need to solve the traffic allocation for the endpoint pair given the bandwidth allocation generated in the first layer. For a specific pair, given the bandwidth allocation generated in the first layer and a set of bandwidth demand from the endpoint pairs, and the max endpoint flow problem is to select a subset of the bandwidth demand whose total traffic is close to without exceeding the given bandwidth. This problem is an NP-hard problem. We propose a novel semi-dynamic approach, fast SSP, to solve it. The audience can refer to our paper for more details. To address challenges at data plane, we leverage the ePBF to handle the individual traffic flow. The ePBF enables the users to customize complex operation in the kernel space to trace the packet. Each ePBF program is running in the kernel space and should be attached as the hook, which will be triggered by the event. There is the ePBF map, which stores the ePBF program states, allowing communication among various ePBF program and between ePBF program and the user space process. Firstly, we identify the traffic flow to collect the process ID and the instance ID when the instance runs the process. Then store them in the map, and when the process creates the socket, we can collect the 5 tuple of the packet and the process ID. And with this information, each 5 tuple and instance ID of a can be accurately mapped to its originator virtual instance. We then attach the ePBF program at traffic control hook to collect the traffic volume of each 5 tuple. Based on the map of instance ID and 5 tuples stored, the endpoint agent will periodically initiate a user space process to collect flow data. Once the centralized controller calculates the optimal path for each instance after T optimization, it will notify the endpoint agent to initial. It will notify the endpoint agent to initiate a process to store the instance ID and packet path in the ePBF map. After receiving the packet, the ePBF program attached as a traffic control layer will firstly capture the 5 tuples and the optimal path of the packet, and the path of packet is inserted into the packet header. Specifically, we let the segment routing inserted after the feature line header, and in this header, the hoop array is a sequence of next hoops specifying the detailed paths of the packet traversing the WAN. The router in the WAN profiles the packet and obtains the hoop information to forward the packet to the optimal path. Okay, we finally present the gain of the MegaTE. We obtain the traffic from the production endpoint and evaluate the performance by increasing the number of endpoints. We compare MegaTE with existing schemas such as NC Flow and TO. We observe that for TO and NC Flow, it takes 5 seconds to complete the T computation. However, in MegaTE, it can support more than 22,000 endpoints with a similar T runtime, supporting 20 times larger network topology. Meanwhile, MegaTE supports a satisfied demand that is close to optimal, indicating the superiority of our algorithm. In failure scenario, we observe that when the network topology becomes larger, the performance gain is larger. The main reason is that MegaTE can quickly react to the network failures. Finally, we have deployed the MegaTE in production to serve the cloud tenants. We compare it with our traditional approach, which doesn't differentiate the queues class of the flow. For those time-sensitive applications, we observe that MegaTE can correctly allocate the traffic to the optimal path, reducing the packet latency. As for application in the cloud, MegaTE can appropriately allocate the network traffic to the path meeting its queues requirements. We observe that for higher priority application 6, the service level agreement is 4.9 and 5, greatly exceeding its requirement. Okay, finally, MegaTE is the first of its kind system to satisfy needs of each fine-grained traffic flow. MegaTE re-architects the T control loop. MegaTE is built on the synergy between the control plane and data plane. Simulation results and production results show the superiority of the MegaTE. That's our thank you.
Hi, thank you for this. I really like some of the underlying intuitions here. I guess it's a 2 or 3 part question. And this might be rather naive. Why do you need the 5 tuple instead of just a 3 tuple? Why do I need the ports if I'm running between end hosts? It's the first.
Yeah, since inserting the flow entries in the router is not possible to solve to address the millions of cloud applications. So we need to insert the routing information before the packet of the virtual instance leaves the server.
Okay.
Yeah.
So then presumably this works for long duration flows. I guess it wouldn't really work for very short. And then is it affected by the short duration flows?
Both of them is okay. Both of them, both of long and short connection can be addressed.
Using this. Okay.
Thank you.
So I have another question is about the topologies you're using for the evaluation. Can you say how you built them, what properties?
The topology is detailedly presented in the paper, but I can we firstly obtain the network topology at the site level, such as B4, and then we will insert a number of endpoints at each router site, such to construct the final topology.
Okay. And then how do you measure availability?
Okay, this is a good question. The application availability is monitored in the Tencent cloud for a long time, so it will report the application availability. We just collect this data.
But so this means you're looking at packet loss for availability?
Yeah. The availability is the time the service is satisfied. The time period the service is satisfied, and we just collect from our Tencent cloud. Yeah.
Okay, thank you.
Okay, thank you very much.
Hi, Brighton Godfrey from UIUC and Broadcom. Can you talk a little bit about the interface between the application and the network, how the application says what it needs, how it communicates that, and if there's are there incentives issues there? Do you let applications do whatever they want, or is it entirely out of band?
Okay, the applications of we just provide the network resource for our Tencent Cloud application. So the application is defined by our Tencent Cloud. We just provide the network infrastructure. So the detailed deployment of the application is not done by our team. Yeah. So, but we will measure the application service level agreement from we have the monitor system. Yeah.
So in other words, do you mean that the applications here are internal cloud applications, and it's not, this system is not used?
Yeah,
by
we have measured part of our internal applications. Yeah, part of our we don't measure the application from TNARS. Yeah.
Thanks.